welcome to another optimization example. So in this example, you are designing a new container for a company. The container has to have a cylindrical base, which must be at least 4 centimeters tall, and a hemisphere top, which you can see I've drawn a diagram of this container. You have 200 square centimeters of material to use. What is the maximum volume container you can make? And what dimensions give that optimal or maximum volume? So just going through making some notes for ourselves. The goal is to maximize volume. Some limits we have. The height is at least 4 centimeters. So I'm going to go ahead and label the height H. And then I'm going to label the radius while we're at it. So the limit is that the height is greater than or equal to 4 centimeters. And we also have that the surface area is 200 square centimeters. So with our height and radius, we can go ahead and create a formula for the volume. We can also create a formula for the surface area, and we can figure out what those limits correspond to, either in height or in the terms of the radius. For our formula, our volume formula, what we're trying to optimize, we're going to have to build this formula. So we have the cylinder. And we will have that half sphere or hemisphere up top. So the volume of the cylinder is the area of the base, which is pi r squared, then times the height. So we have pi r squared h. So that we are going to add the area of half of a sphere with still radius r. So we have half times the volume of a sphere is 4/3 pi r cubed. So what we are looking at then is we have the volume is equal to pi r squared h plus 2/3 pi r cubed. So this is our volume formula. Then our surface area So again, looking back at our limits, we still had r is greater than or equal to 4. H is greater than or equal to 4. And then our surface area was 200 square centimeters. So our surface area formula, we'll have the bottom, which is a circle. We'll have the sides, and then we'll have our half sphere. So we have 3 components here. The bottom is just a circle. So the surface area is just pi r squared. The sides are just, if we cut down the one side and opened it up, we just have a rectangle. And the length of the rectangle will be the circumference of that circle, and the width or height will be height. So the circumference of the circle is 2 pi r, and then times height for the height of the cylinder. And then the half sphere, we will do 1/2 times the surface area of the sphere is 4 pi r squared. So if we plug in our 200, we'll have 200 is equal to pi r squared plus 2 pi rh plus 2 pi r squared. Or in other words, 200 is equal to 3 pi r squared plus 2 pi rh. So when we do an optimization problem, we're going to need to solve one of those variables in terms of the other. I strongly recommend solving for h in this problem because it will be a lot easier than solving for r. So if we solve for h, we wind up getting that h is equal to 200 minus 3 pi r squared, and then we would have to divide by 2 pi r, and that would be h. So we now can write our volume formula solely in terms of radius. We also need to know what our limits are. So note that r has to be greater than or equal to 0. Well, it doesn't really make sense to be 0, but we'll go ahead and use it. And then we need to figure out h greater than or equal to 0, what that translates to. Sorry, h greater than or equal to 4. We need to figure out what that translates to. So that would be that 200 minus 3 pi r squared over 2 pi r is greater than or equal to 4. R is assumed to not be negative, so we can go ahead and just multiply by 2 pi r. So we have 200 minus 3 pi r squared is greater than or equal to 8 pi r. And then if we rearrange this, we're looking for positive 3 pi r squared plus 8 pi r minus 200. We're looking for where that is less than or equal to 0. So this is moving everything over to the right and then writing the equation kind of backwards. Right. So we can figure out where this is equal to 0 using, I'm just going to use the quadratic equation. I'm not going to factor with pi's involved. So r would be equal to, we're using the quadratic formula or quadratic equation. A is equal to 3 pi, B is equal to 8 pi, and C is equal to negative 200. So we have R is equal to negative B, so negative 8 pi, plus or minus the square root of B squared, 8 pi squared, minus 4AC, so minus 4 times 3 pi times negative 200, all over 2a, so all over 2 times 3 pi. And this winds up simplifying to negative 8 pi plus or minus the square root of 64 pi squared plus 4 times 3 is 12 times 200 would be 2400 pi all over 6 pi. And if we go ahead and plug that into a calculator, I'm going to get the number and then store it. We wind up getting, this is negative 8 pi plus or minus the square root, I did that part. This is negative 8 pi plus or minus 90.396 all over 6 pi. I'm looking for a positive r. I don't care about the negative so much. So we're going to get some negative number if we do the negative 8 pi minus, or the positive number will be up top, we will have 65.263 all over 6 pi. And again, we'll get some negative number. Or if we divide by 6 pi, 3.46 something. So if you think about, we're looking for where this is, the quadratic equation is less than or equal to 0. And it's equal to 0 at some negative number, whatever that is. And then again at 3.46. And then if we look at the original equation, 3 pi r squared has a positive 3 out front. And so quadratic parabolas open up if they're positive. So our graph would look like this. And so where this is less than or equal to 0, which is what we want, is before the 3.46. Right? And so the limits on R will be 0 is less than or equal to R is less than or equal to 3.46 approximately in centimeters. So in this problem, we are, technically it'll be less than, but that's okay. We're essentially looking at, sorry, it'll be 0 is less than R technically, since it doesn't really make sense to not have any width to our container, but we'll leave it at this for now. Again, this one here came from H being greater than or equal to 4. Okay. So we only are concerned with R between 0 and 3.46. Anything outside of that doesn't meet the limits for our can. So now we're going to go back. So looking back at our volume formula. I apologize for the back and forth. We're doing these problems are just kind of a lot of back and forth as you're figuring out what you're working with and what your limits are. I like to have kind of all the needed information jotted down immediately at first, just so that you have it written out. But if it's easier for you to say only work with the limits first, and then only work with your limitations first. This was supposed to say limit. If it's easier for you to only work with your limitations first and then create the function that you're trying to optimize, that's fine as well. So again, I'm just going to take a picture of, or copy what we had. So the volume formula that we'd worked out, we had volume was equal to pi r squared h plus 2/3 pi r cubed. So let's go ahead and add that down here. So it's 2/3 pi r cubed. And then the other piece of information we had was that h was 200 minus 3 pi r squared all over 2 pi r. So at this point, then we can go ahead and plug in. So we have volume is equal to pi r squared times 200 minus 3 pi r squared all over 2 pi r plus 2/3 pi r cubed. If we multiply in that pi r squared and break up our fraction, the 200 pi r squared over 2 pi r would leave us with 100 r. Then we have minus, I'm just gonna cancel. So this pi will cancel with the pi down below, and one of the r's will cancel with the r down below. So the only thing we're really dividing by is 2. So if we do 200 divided by 2, we have 100, and the r is being distributed inside. And then we will have 3/2 pi r cubed remaining. So we are subtracting 3/2 pi r cubed, then adding 2/3 pi r cubed. Or if we want to put this all together, volume is equal to 100 r minus, that'll be 9/6 plus 4/6 is minus 5/6 pi r cubed. So we know our endpoints. So now our goal is to optimize. We need our endpoints. So those were r equaling 0 and r equaling approximately 3.46. And we also need critical values. So everything before this point was set up. At this point, we're down back to chapter 3 now, just doing our optimization on a closed interval. So for our critical values, we'll take the derivative. So we have v prime is equal to 100 minus, let's see, power rule, that would become minus 5/2 pi r squared. And if we set this equal to 0 or undefined, there is nowhere that this is undefined, so we're going to do equals 0. So what we wind up with is 5/2 pi r squared is equal to 100. Or pi r squared is equal to 100 times 2/5, which is 40. R squared is equal to 40 over pi. Or r is equal to the square root of 40 over pi. I don't need the negative version because we know that r is between 0 and 3.46 is what we're interested in. Technically, the negative version is a critical value, just not in our window. So if we go ahead and take this square root of 40 over pi, this winds up being plus or minus 3.568. Both of these are outside of our closed interval. So both of these are outside the interval 0 less than or equal to r less than or equal to 3.46. And so we don't need to pay attention to them. These are the only places that we care about. So we won't use the critical values. We're just going to ignore the critical values. So that means that the only 2 places that we have to check for optimization are at our 2 endpoints. So if we do our quick check, so we're going to check V at all points of interest. So for our radius, The two we're doing are 0 and then 3.46 something. And again, our formula for volume was 100R minus 5/6 pi r cubed. I can tell you right off the bat that for R equals 0, the volume is 0. If we plug in that 3.46, we wind up getting a volume equal to 237.57 cubic centimeters. So this comes again from using that R equals 3.46. We get our volume, and this 3.46, we actually already know the H corresponding to it. So here's our maximum. So this is our max volume. And then 3.46 for R, this value came from H equaling 4. So what we wind up getting is the maximum volume is 237.57 cubic centimeters, which occurs with cylinder height 4 centimeters and radius approximately 3.46 centimeters. So this is an optimization problem where we're dealing with volume and surface area. This one's two objects put together. Sometimes you'll just be able to work with something like a cylinder, which you have on your homework for this week. When you're given additional limits beyond the usual greater than or equal to 0, sometimes it's a little more work to solve for those limits, as we saw in this problem. But once you have the limits, then it's just a standard optimization problem of any function.